Download this code from codegive.com, link in the description below. Consistency and Replication in Distributed Computing, a comprehensive tutorial. Distributed computing systems, where data and processing are spread across multiple nodes, offer significant benefits like high availability, scalability, and fault tolerance. However, they also introduce complexities, particularly concerning consistency and replication. Replicating data across multiple nodes is essential for these benefits, but it creates the challenge of ensuring that all replicas remain consistent, meaning they reflect the same state at a given time. This tutorial will delve into the concepts of consistency and replication, explore various consistency models, discuss common replication strategies, address potential issues, and provide illustrative code examples to solidify your understanding. Introduction: Why consistency and replication matter. Availability. Replication allows a system to continue functioning even if some nodes fail. If one replica becomes unavailable, other replicas can still serve requests. Fault tolerance. Replication helps tolerate node failures. Data isn't lost when a node goes down because multiple copies exist. Scalability. Replication enables distributing the load across multiple nodes, improving system performance by handling more concurrent requests. Read requests, in particular, can be easily scaled by directing them to different replicas. Reduced latency. By placing replicas closer to users, geographically, read latency can be significantly reduced. However, achieving these benefits requires careful consideration of consistency. When data is modified, changes must be propagated to all replicas. The delay in propagation can lead to inconsistencies, where different users see different versions of the data. 2. Defining consistency models. Consistency models define the guarantees provided by the distributed system regarding the order and visibility of writes across different replicas. They represent a contract between the system and the application. Stronger consistency models offer more guarantees but may come with performance trade-offs. Here's a breakdown of common consistency models. 1. Strict consistency. Ideal but impractical. This is the strongest possible consistency model. It guarantees that any read to a data item will return the value of the most recent write to that data item, across all replicas. This implies a global, instantaneous view of the system state, which is impossible to achieve in practice due to network latency and the speed of light. 2. Sequential consistency. All operations are executed in some sequential order, and each process, client, observes the operations in that same order. It doesn't necessarily require operations to be executed in real-time order but guarantees that all processes see the same history of operations. This is stronger than causal consistency. 3. Causal consistency. Writes that are causally related, example write B depends on the result of write A, must be seen by all processes in the same order. Writes that are not causally related can be seen in different orders by different processes. This is a weaker form of consistency that provides a more flexible approach. 4. Eventual consistency. This is the weakest consistency model. It guarantees that if no new updates are made to a given data item, eventually, after some time, all accesses to that item will return the last updated value. It allows for temporary inconsistencies between replicas. Many NoSQL databases employ eventual consistency for scalability and performance. Read your writes consistency. A guarantee that after a process performs a write, any subsequent reads by that process will see the value of that write or a more recent write. Session consistency. A user's session remains consistent. This might involve read your writes, monotonic reads, a process never sees an earlier version of the data, and monotonic writes, writes from a process are applied in the order they were issued. 5. Linearizability, atomic consistency. All operations appear to have happened instantaneously at some point between their start and end times. This is a strong consistency model, often confused with sequential consistency. However, linearizability also requires that the real-time ordering of operations be preserved. It provides the illusion of a single, centralized data store. Choice of consistency model **. The choice of consistency model depends on the application requirements. Strong consistency essential for applications requiring strong data integrity, such as financial transactions or banking systems. Weaker consistency suitable for applications where temporary inconsistencies are acceptable, such as social media or content delivery networks. They often prioritize availability and performance. 3. Replication strategies. Replication strategies dictate how data is copied and maintained across multiple nodes. 1. Active replication, state machine replication. All replicas process every request. This approach provides high fault tolerance, as all replicas are always up to date. However, it requires a consensus mechanism, example Paxos, Raft, to ensure that all replicas execute requests in the same order and agree on the results. This strategy is suitable for applications where strong consistency is paramount. 2. Passive replication, primary backup. One replica is designated as the primary, which handles all write requests. The primary then propagates the changes to the backup replicas. Synchronous replication. The primary waits for all backups to acknowledge the update before confirming the write to the client. This guarantees strong consistency but can lead to high latency if backups are slow or unavailable. Asynchronous replication. The primary acknowledges the write to the client immediately, without waiting for the backups. This provides low latency but introduces the risk of data loss if the primary fails before replicating the changes. 3. Quorum-based replication. Write operations are considered successful only when a certain number of replicas, the write quorum, W, have acknowledged the write. Read operations are considered successful only when a certain number of replicas, the read quorum, R, have returned the same value. To ensure consistency, the sum of the read and write quorums must be greater than the total number of replicas, nr plus wn. Example if n equals 3, setting r equals 2 and w equals 2 ensures strong consistency. Any read operation will see the latest write operation, as at least one replica will contain the latest value. 4. Handling replication conflicts. When multiple replicas allow write operations, multi-master or masterless setups, conflicts can arise if different replicas update the same data concurrently. Conflict resolution strategies are crucial. 1. Last write wins, LWW. The write with the latest timestamp wins. This is a simple approach, but it can lead to data loss if the timestamps are not perfectly synchronized or if there are clock skews between nodes. 2. Vector clocks. Each replica maintains a vector clock, which is a vector of counters, one for each replica. When a replica performs a write, it increments its own counter in the vector clock. The vector clock is then attached to the written value. When reading, conflicting versions are detected by comparing the vector clocks. If two versions are concurrent, i.e., neither is a descendant of the other, the application must resolve the conflict. 3. Conflict-free replicated data types, CRDTs. These are data types designed to guarantee that concurrent updates will always converge to the same value, regardless of the order in which they are applied. Examples include grow only counter, G counter can only be incremented. Asterisk add wins set asterisk when adding and removing the same element concurrently, the add operation wins. Asterisk last write wins register asterisk similar to LWW, but designed for CRDT applications. For application-specific conflict resolution asterisk the application can implement its own conflict resolution logic based on the specific data and requirements. This allows for more fine-grained control over how conflicts are handled. V-code examples, Python. Let's illustrate some of these concepts with Python code examples. These are simplified examples to demonstrate the core ideas. In a real-world system, you'd use a distributed data store or a specialized library. 1. Primary backup with asynchronous replication ***. Key improvements in this example. Threading uses threading to simulate the asynchronous replication process. The _replicate _to _backup function is executed in a separate thread, allowing the write _primary function to return immediately. Event the backup _updated event is used to signal when the backup has been updated. This allows the main thread to wait for the update to complete, although in a real system, you'd likely have more sophisticated strategies than explicit waits. Locking the threading .lock is used to protect access to the shared data, primary _data and backup _data. This prevents race conditions and ensures that updates are applied atomically. Clearer output the print statements are more informative, showing the data being written and read by both the primary and backup. Timeout added a timeout to the backup _updated. Wait, to prevent the program from hanging indefinitely if the backup fails to update. 2. Quorum-based replication, simplified. Key improvements in the quorum example. Version tracking maintains self.versions to track the version of each replica. This is crucial for determining which replica has the most recent data during reads. Quorum check explicitly checks if the read and write quorums are met before returning success. Rollback on write failure if the write quorum is not met, the code now reverts the successful writes, ensuring consistency. This prevents having some replicas with the new value while others have the old value. Read consistency check during the read, the code checks if all the values returned by the read quorum are the same. If they are not, it indicates an inconsistency, and the read is considered to have failed. Replica availability the read operation first determines which replicas are available before attempting to read. This is important because replicas might be temporarily unavailable due to network issues or node failures. Clearer error handling improved error handling with informative print statements to indicate the reasons for failures. Sorting by version before reading, the available replicas are sorted in descending order of version. This ensures that the read operation prioritizes replicas with the most recent data. More robust handles potential exceptions during the write operation and returns false if the write quorum is not reached. Reset replicas added code to reset the replicas and versions for testing purposes. 3. Eventual consistency with last write wins, LWW. Improvements in LWW example. Timestamping adds timestamps to the stored values, which are essential for the LWW conflict resolution strategy. Conflict resolution includes a resolve_conflicts method that merges data from another store, resolving conflicts based on the most recent timestamp. Locking, adding the lock ensures atomicity of the data access. Clear output, adding print statements for debugging and understanding the data flow. These are basic examples to illustrate the principles. In a real distributed system, you would use specialized libraries and frameworks for implementing replication, consensus, and conflict resolution. 6. Common issues and challenges. Network partitions, split brain. When the network is partitioned, different groups of nodes might be unable to communicate with each other. This can lead to data inconsistencies if writes are allowed in both partitions. Solutions involve employing fault tolerance and failure detection mechanisms. Clock skew. In a distributed system, clocks on different nodes may not be perfectly synchronized. This can lead to incorrect timestamp-based conflict resolution. Solutions include using network time protocol, NTP, or logical clocks. Performance trade-offs. Strong consistency models often come with performance penalties. The need to synchronize updates across multiple replicas can increase latency. It's essential to choose a consistency model that balances consistency requirements with performance goals. Complexity. Implementing and managing distributed systems with replication and consistency is inherently complex. It requires careful design, thorough testing, and robust monitoring. Data loss. Asynchronous replication offers lower latency but introduces the risk of data loss if the primary node fails before replicating changes. This requires a well-designed failover mechanism to minimize data loss. 7. Best practices. Understand your application requirements. Carefully analyze the consistency requirements of your application. Don't over-engineer for strong consistency if it's not needed. Choose the right consistency model. Select a consistency model that balances consistency with performance. Implement robust failure handling. Design your system to handle node failures gracefully. Use proven technologies. Leverage existing distributed databases and frameworks that provide built-in support for replication and consistency. Monitor your system. Continuously monitor your system's performance and data consistency. 8. Conclusion. Consistency and replication are fundamental concepts in distributed computing. Understanding the different consistency models, replication strategies, and potential issues is crucial for building robust and scalable distributed systems. By carefully considering your application's requirements and choosing the right technologies and techniques, you can leverage the benefits of distributed computing while mitigating the challenges associated with data consistency. Remember that there is no one-size-fits-all solution, and the best approach will depend on the specific needs of your application.